Now, a lot has to go into the design and development of general QKD systems or BBM92 key distribution systems. And the first part is, where are we going to implement it? The obvious choice in many cases will be to use an existing fiber optic network and to plug in commercially available optical devices into that network. Once those optical devices are in the network, you can run it and you can start establishing shared secret keys at your two endpoints. But the big question is, if you have a network, how well will a particular device or devices perform in that network? So to approach this problem, there's kind of two main approaches we can take. The first being theoretical analysis. With theoretical analysis, you would take all of the hardware specifications and characterizations about your fiber network and the devices you want to use. Then you'll use this characterization to estimate the quantum bit error rate and the secure key rate using a theoretical model. This theoretical model might be derived from literature or might be derived using your own insights and assumptions. Now, theory really excels when systems are simple or emit a lot of symmetry. This makes the mathematics more simple and easy to work with. And it is useful because it can characterize systems that cannot be simulated. Theory can still operate when we have infinities. Simulation doesn't really work, or computers don't really work when you have to store values that are infinitely large, for example. Now, on the other hand, simulation analysis starts from the same point as theory. You start with your hardware specifications and characterizations, and you want to take those specifications and estimate the quantum bit error rate and secure key rate using simulation. Now, simulation is a little bit different than theory. Simulation excels for complex systems that require tedious calculation to model. So you have a computer doing all of these calculations for you. You just have to set up the simulation, and the computer will handle all of the number crunching. Now, simulation works really well when it operates in conditions or settings where theoretical assumptions do not hold. As I said before, when you're working with theory, you like to have some assumptions that will lead to simplifications in your theoretical statements. Now, if those assumptions don't hold, your theory will no longer hold. However, in simulation, you can often get around these assumptions by modeling the system more explicitly and letting the calculation and simulation all be taken care of by the computer. So this lets you explore messy situations that are more realistic than theory can accommodate. So the way to think of both theory and simulation is that they're actually complementary techniques. The advantages of one are not the advantages of the other, so they aren't really in competition. You should be using both of them to help design real-world quantum networks.